Is Jonathan here? No. Can somebody get it?
Sure.
Yeah, we will. Say it again?
You're just by your desk there.
Okay. Well, we want to welcome our guest, Rick Lyons from NASA Auto, and he's going to show you the man. Yeah, because we want to actually use this opportunity to probably begin our Industrial Institute of Optics. So this could be a history day for us. Greg and I have been floundering around for quite a while trying to get it going. And we said, well, listen, if we just started, we'll get things rolling. And everybody's welcome to sit in because I'm hoping he's going to explain some of what our parts do even. So that's going to be exciting, you know? And we want to make sure everybody's aware. I don't think I did a great job announcing all this. A lot of this is just coming together just because of schedules and everything. We had a lot going on this week. And some of the vacations are starting and people got sick and in and out. But one thing, we can get going, we'll have a good time. And I'd like, Pastor Anderson, would you stand up and just say a little prayer like you always count on you to cover the...
And thank you, Lord, that I was able to stand up. And for a great meal, and for the vision that Joe has, and for the privilege of taking part in these things. And for today, for our guests, we give you thanks, and we praise your name. Amen.
Okay, Greg, if you want to come up and say a little bit.
Well, say a little prayer.
Yeah.
Well, General, thank you for the good food from everybody. Well, I want to introduce you the guy that I worked with for 7 years. Well, we spent some time in NASA. Enrique is a wonderful guy. He is a mathematician, and he has a lot of honors. I believe you have more by this time, right? Those plates on your board. So it's a little bit boring to go through that. But Rick was on a team actually to reconstruct the images from Hubble, and we heard from astronauts how they were physically correcting Hubble by sending the team there and installing those correctors. Very hard mission. And Rick did the same task pretty much on the ground. He was trying to mathematically recover the wavefronts. Took him, what, 20 years? No, by this time, you won't face diversity, what, for more than 20 years?
Yeah, I still work on it.
Still work on the test, but the test that he was working before, helped to actually reconstruct the images. And the interesting part of it was that he was able to get more information from Hubble than if the mirror was absolutely perfect. And it's a great pleasure to introduce him here today. And the topic of his talk is right there. It's extraplanar chronography. And everything else, I think, Rick, you will explain yourself if you don't mind.
All right, thanks, Greg.
Sure.
You can hear me all right through the mic. How do I advance the slides?
Oh,
Yeah, thanks, Greg, for the introduction and Joe.
sorry, sure.
Yeah, I know Greg.
Finish it, this starts.
Okay. Oh, I can just come over. Okay. All right, thank you. Yeah, Greg and I used to work together at Goddard on imaging and difframetry test beds, and I guess it must be 7-8 years ago now. And we had a lot of fun. We wrote research proposals, wrote papers, built up the test beds, tried experiments in the lab, and so on. But NASA's kind of a changed place these days. Things are all about bringing in large funding grants to fly missions to actually do this large-scale science. And today I'm going to talk about exoplanet coronagraphing, which is really one of the holy grails of modern science. This is really an area where we want to search for life elsewhere in the universe or outside of our solar system and even within our solar system. And this is one approach. So now life, you could put a double quote around that because there is no hardcore definition of what is life. We think we know what it is on Earth, but we really only have one example. It's all kind of DNA, RNA-based life on our planet. And so based on that, we only have our current knowledge as we kind of venture out there and look further away. And so the main things we want to look at, the main things we want to look at would be to detect terrestrial, which are Earth-like planets, around the nearest couple of hundred stars. And then, oh, it's green. Not comfortable holding the mic. Well, essentially we want to detect Earth-like or terrestrial-like planets around the nearest couple hundred stars. But the actual real important part of the science comes in from what's known as spectroscopy, or looking for biomarkers. Now, biomarkers are things like liquid water, CO2, methane, oxygen, and ozone. And things like methane, CH4, after a few hundred years in our atmosphere, if there was no life, it would all bleed off. It would actually be broken down by the ultraviolet light in our sun and be gone. And so it's not so much that you want to find methane or oxygen, you want to find that they're in non-equilibrium ratios relative to each other. So you want to look at spectroscopy. Now if you look at a planet around a nearby star, it's in 10 parsecs, or about 26 light years. The problem you run into is the planet is extremely close to the star. You can't really see it too easily on here, but this is just a kind of a cartoon of our solar system. This would be our sun, and these would be the planets. So we're specifically looking for planets in this green band known as the habitable zone. The habitable zone, the inner edge, is defined where no water would exist on the planet because it would all bleed off because it would be too hot. So it would basically be vaporized. And then everything at the outer edge of the habitable zone would be where water would be frozen or always in the ice phase, unless there was some internal geophysics going on, like volcanic activity or so, which actually happens in our solar system on some of the moons of Jupiter. And so the near terms, this is the ultimate science goal. Now how do we do this? We don't really know how to do this yet. We know how to do the terrestrial to detect them. How to actually characterize them in spectroscopy needs an incredibly large telescope because you have to collect a lot of photons. Now if you look at a star, say a fifth magnitude star, you're getting billions of photons per second, about 10 billion photons per second in a 4-meter aperture telescope. But you only get 1 photon per second from the planet. So in order to unambiguously detect that 1 photon, 1 photon per second or so, you have to integrate for hours. Now if you're trying to distribute this out spectroscopy, if you're looking for these lines, it's going to be weeks. So you're going to have a large telescope that points at a single target and is ultra stable for many weeks on end. You're only going to be able to do very few targets per year. And then you may be in a situation where you find that there is none of these biomarkers, and then you've used up your whole 5-year mission life. So then you would just prove the null result. You haven't proved that life doesn't exist, but you haven't detected it either. So this is sort of a conundrum that NASA finds itself in, puts together these review panels to review this. Now, more realistic and the nearer term science goals are to look what are known as Jovians or Jupiter-like planets and super-Earths, and dust and debris disks, and statistics of exoplanets. So there's a mission up there now known as Kepler, and Kepler basically looks at a small patch of sky, a few degrees wide, just off the galactic plane, and it just looks for transits. Transits is when a planet passes in front of its star. If you just integrate all the light, there's a small dip in the light curve, about one part in 10 to the 6, and they've already detected 600 or 800 new planets, of which about 10% of those are believed to be about Earth mass. Now that hasn't been confirmed yet, but those are kind of the estimates. And so that nails down one of the critical unknowns, ATIS of Earth. So what's the probability that a given star has a terrestrial planet? If none of the nearest planets, our nearest stars, have any terrestrial planets, you could be in a situation where you design and fly a $5 billion mission and never find one of these planets. So you have to get a handle on the dimensionality of your parameter space and kind of narrow it down and bound it. And a terrestrial planet in the habitable zone is about 10 orders of magnitude dimmer than its parent star, and about 10 to the 7th, that's invisible or reflected light, but it's about 7 orders of magnitude dimmer in infrared light. So it seems easier to detect in infrared light, but there's a complex phase space between these two. Invisible light, the wavelength is 500 nanometers, where in infrared it's 10 microns, or 20 times longer, so you need an aperture that's 20 times larger in order to get the same inner working or the same resolution for the telescope. So that's much harder, but you could do it interferometrically. And these two approaches have been traded back and forth now for 10, 15 years, close to 15 years or so. Okay. Now, to sort of put the problem in kind of an optical perspective is if we would just look at Hubble. Now, if we were to just focus, point at a star system at 10 parsecs or 26 light years away, and within 10, well, out to about 30 parsecs is 8,000 star systems. In 10 parsecs is maybe close to 1,000. Of course, it's scaled roughly as the cube.
I'm sorry, I don't know if your pointer's working.
It works when I just
Yes, it was.
green. That's the problem. I can actually just point to it up here.
That would be good. Thank you.
Okay. So if you look at Hubble, the Hubble Space Telescope, you would end up, if you focused on a star, you'd get an image of the star in these bright diffraction rings. That's just caused by the edges of the aperture starting to diffract light out, because we don't collect all the light from the star, we only collect a piece of it with a telescope. And so our whole star system at 10 parsecs would fit into that bright star.
Nice.
Yes. Actually, I'm much more comfortable. Our whole star system, our whole solar system would fit into the core of the point spread function or the airy disk. And so this is really bright relative to the planet. You wouldn't be able to see anything. You just see one bright dot. So how do you get rid of this diffraction and all that's glare? That's the critical problem. That's what a coronagraph does. It gets rid of the corona of this. And so how much does it have to get rid of it? If I take a slice from left to right through here and plot it, you end up with this rippling function. And then if I was to look for a planet out there, it also has that same rippling function. But the difference between them is 10 orders of magnitude on a log scale. And then they're only separated by 1/10 of an arc second, or 100 milliarc seconds.
It's a huge red, I'm not sure.
It'll probably reflect in this one.
It reflects from the skin.
Yeah. If you want to detect something that's 10 orders of magnitude dimmer separated by just a couple of pixels on the screen, which map to the sky as 100 milliarc seconds or 1/10 of an arc second. And arc seconds are 3600th of a degree, and so we want to be at 1/10 of that number. So you have to point and hold your pointing that whole time for this. Now, coronagraph in principle mathematically works perfectly. I mean, you can design one that will do this, and I'll show an example of it. A number of things can go wrong with it. The first one is what's called speckle. The telescope itself, when you polish an optical surface, it has coatings on it, and the shape, can deform and has little bumps and stuff, aberrations, which show up as wavefront errors. Now, if you perfectly correct the wavefront with a telescope, you only get about 8 orders of magnitude of contrast. You really need another factor of 100. So then the next thing it becomes sensitive to after perfect wavefront correction is amplitude errors. It's about 40 times less sensitive to amplitude errors. So once you bring that down, you get about almost 2 orders of magnitude of gain just correcting the amplitude. So now you're better than 10 to the 9th contrast. Your requirement is 10 to the 10th. So now the next step is polarization. So you have to have a sensing and a control system which senses amplitude, phase, and polarization and corrects them simultaneously. And if that's not hard enough, you have to do it over a broad range of wavelengths, because if you did it narrow band, you wouldn't get enough photons to actually sense anything. So you have to do this over a couple of 100 nanometer band pass. You have to do an achromatic wavefront control. Now, there's a couple of schemes to do that. This kind of shows visually with some actual real, ground data on the left and a Hubble image on the right, what speckle looks like. So this was Christopher Marois' Keck telescope image, and then his Gemini image of HR 8799, which is a star system at about 30 parsecs away. And they see 3 planets, and it's actually been confirmed a number of times with different ground telescopes. Now, if you look at these planets, these are extremely bright. And they're almost like brown dwarfs, which are stars that didn't really ignite. They're brighter than Jupiter. And this is in reflected light, but they're in the near IR, around 2 microns, 2.2 microns or so. But the distance to the closest one is 25 AUs. And we're, by definition, 1 AU from our sun. So the closest planets 25 times further out are about the distance of Pluto is, or 5 times the distance of Jupiter. Now, this is speckle. This is caused by the wavefront, the amplitude, and the polarization errors in your optical system. And you can see it's chromatic, because this is an RGB image where there's 3 separate spectral filters put together. You can see that the speckle structure varies chromatically, and it varies with time, because even in a space telescope, the sun angle's changing over the course of days or weeks as you're looking at a target. So it's seeing a slightly different thermal environment. There's spinning wheels in there which keep it pointed, and that's coupling to the structure and causing vibration and things to move around, which causes the optics to shim against each other and so on. You have to sense and control that. And in space, along the ground, it's even worse, of course, because now you have atmospheric turbulence and atmospheric scintillation, which is amplitude errors passing through the atmosphere, and you get some small changes in polarization, and the atmosphere also varies chromatically with different wavelengths, too. So it's an enormously hard problem, which still, for detecting terrestrial planets, is probably still 20 plus years in the future or so. But we have NASA has, funded a whole series of studies for different instruments and different concepts. And so what we do is different groups develop a design, and then you flow this design, you flow the science requirements to a system and subsystem component level, assess the state of all the technologies, what would have to be done to push all the technologies up to the level needed for flight, try to cost that out, and you iterate this back and forth. These are typically done in 10-year cycles, and then they're collated in a decadal survey, which just occurred in 2010. And so the decadal survey is when the National Academy of Sciences puts together a review panel, and they review all the big science for the entire United States. And then they make recommendations, and they have different subcommittees, and there was an astrophysics one. So they recommended that the exoplanet science for terrestrials is still 10 years, still has 10 years before we recommend to go forward for a mission, which is about right. That's what most people would agree. And then they put up technology development funds to fund these specific technologies. That's about where we are now. We're expecting somewhere 15 to 40 million per year for the next 10 years for specific technologies. So how does a basic Leo coronagraph work? Leo was a solar astronomer in the 1930s. Yes?
Sorry, can I ask you something?
Yes.
On the previous screen, there was a diameter. What was that, AU?
is that Jupiter's orbital thing?
Oh, that's the diameter of Earth's orbit around the sun. If it was on that scale. You took our star system and moved it out to the same distance as the star system. And then if you were looking at it face on, then that would be Jupiter's orbit around the sun. 5 AU. An AU is an astronomical unit. It's by definition the distance from our sun to the Earth, the mean distance. And so that's also the definition. It comes from the definition, it comes from an arcsecond. If you took our star system, looked down and face on, you saw our sun and Earth, and then you moved it, kept moving our star system further away. It will do this until the angular separation between the star and the Earth is 1 arcsecond, and that's the definition of that distance, 1 parsec, which is 26.7 light years, I believe. It just makes scaling units easy, actually. If you work in AUs and parsecs, everything is kind of a natural unit. The basic principle of a Leo coronagraph, well, it goes back to Leo as a solar astronomer in the 30s, and he came up with a method by putting a mask in the focal plane, the diameter of the image of the sun. He could take the light out, but he realized that when he re-imaged the pupil, he ended up with a bright ring. So he just built a mask, and that mask caused the sun plus all its diffraction to go away, and then he saw the solar corona. And it was pretty amazing, actually, at that time. And he, not only did he think this up, he actually did the math, worked it out, modeled it, built it, published papers on building it, and collected the data and published the astronomy papers pretty much almost on his own when everyone was telling him it didn't work. When eventually they could see the coronal jets and outflows from the sun, they had to start believing. It was kind of an interesting story behind that unto itself, actually. But the basic idea is, so you'd have a telescope or an optic, the light's coming in from your star, it's coming to focus. If you would just put a mask in the focal plane that looks like this. And so where it's white, it's perfectly transmitting, where it's dark, it's perfectly blocking in intensity, and it has these ripples like a diffraction gradient. Now this is one special type of mask. There's a whole lore and probably 20 or 30 different designs for these masks. And then you just block that light. And then when you have optics which re-image the primary onto what's called an exit pupil, or also known as the Leo plane, the Leo style. And what you would see now, if there was no star or anything else in there, you would just see this kind of eye shape, which is the sum of 3 circles. See a bright ring, an even brighter ring, and then another third bright ring, just all shifted. Now what this mask does, it acts like a diffraction gradient. Diffracts 3 orders. And so you end up with 3 field components, such that the phasor sum of the field components sums to 0 in this dark mean. So then you just build a mask which masks everything but the eye-shaped region, known as a Leo mask, and then you bring it to focus, and the planet pops up. So mathematically that works better than 10 orders of magnitude. But the problem is, you know, as I said, all the polishing marks and stuff on the mirror surfaces gives you all this leakage they have to sense and control. So in principle, you could do this, and people have built test beds and tried this technique, and they get results when the optics are super stable. But the flaw in this approach is somewhat subtle. It's if you go, okay, all the errors from the telescope in the manufacture of this mask occur in common in all 3 beams which are coming out to the right side here. Now, since all the beams always overlap in 3-dimensional space, they're not spatially separated. That means any sensing and control system has to correct the absolute error of the light going through the telescope and the mask. What you really want to do is split the beams into different paths, put devices in between that only corrects the differential error between them. And so that's kind of the direction a lot of this work's going in. These show some of the 3 of the NASA-funded approaches. This was a filled aperture telescope, just a 1.65 meter. This was for Jovian or Jupiter-like exoplanets. but not terrestrials. This would be a follow-on to the James Webb Space Telescope. This is 9.2 meter aperture, and it uses a lot of legacy to the James Webb primary mirror technology. It's using 1.2 meter segmented primary mirror made out of beryllium or some type of exotic glass, and the whole thing kind of unfolds in space. And then this is Da Vinci, which is Mike Shaw's JPL, which uses 4 smaller telescopes that feeds into a visible knowing coronagraph. Now, 3 main things can be clear from these studies. There were actually 7 studies funded about 4 years ago, or 18 months, with 7 separate non-overlapping teams, and all the results were collated. And the main thing that became clear, in kind of order of precedence, is that future large telescopes are going to have to be segmented or interferometric. The reason for this is there is no rocket that will hold a 9+ meter aperture in. So you're going to have to basically build it in space or unfurl it or unfold it. And so any coronagraph technique that only works with a filled aperture without diffraction structure is non sequitur. You don't really care because it'll never be useful in space. So you have to come up with an approach that works with segment gaps in there. Now the Leo coronagraph does not work with that. As a matter of fact, it fails fairly miserably. It requires a very unobscured aperture. There can't be any hole for a secondary mirror, support struts, or anything. It has to be very clean. And so, or it could work with an interferometric aperture, multiple telescopes which are phased together that interfere coherently. The next main thing was the wavefront control limits the performance of any internal coronagraph. What we found actually, all the teams did various levels of simulations, and it was almost independent of what type of coronagraph approach you use. You still end up with the same sensing and control limits, which kind of made sense if we really thought about it before we did the study. But it was actually kind of empirically, or at least modeling and simulation that was determined. So independent of the approach, you still pretty much have the same tolerances on all your optics and components in there. And then the one which I consider very important at this stage, so these are kind of a given, but this one is still somewhat debated. The control bandwidth, of course, limits the stability of the telescope. It's not that the control bandwidth itself limits it, but if you have a telescope that's varying on the scale of, hours at 15 picometer level. So that's the level of requirement you need. The stability is about 15 picometers per control step. So if you control once per hour because you're collecting the photons and feeding back to your control system, then it's going to have to be enormously stable and enormously expensive and untestable on the ground. Now, if you can go with a system where the telescope's shimmying around and dancing and doing all kinds of funky things, but you can sense it and control it at, say, 100 hertz, then the telescope cost plummets, basically like the cube of that number. So you can actually get away with much lower cost telescopes. So that's kind of a trade space. It's just now starting to be evaluated and opened up. And so we had access to all these studies and we're involved with a number of them. And the approach that I tend to like the best is what's known as the visible knowing coronagraph. Now, I'll show you how that works, but it's the only known approach that works with segmented or interferometric aperture. It also has advantages with respect to sensing and control because it's an interferometer. When you have a coronagraph, when you have the mask, the light which is blocked by the mask is lost from your control system. And so it's absorbed. Now you can put a reflector on it and reflect it around. And I'll explain why that doesn't work very well either, but if you were to absorb all the light, then only the dark light which leaks by the mask is there to sense and then feed back to your telescope. But you're in the situation now as your control system works better and better, it drives you darker and darker, you get less and less photons, so it takes longer and longer per control step. And so those control steps now, instead of go from a few hours, they go to 8 hours. And so that's a non-starter. You can't build a telescope at 15 picometer stability that's stable for 8 hours. At least no one knows how to do that. Now, if you were to reflect the light off, though, and bring it around and then mix it against the other channel, what happens is the fact that it reflects off the front of the mask, and it's only the core of the air disc is a filter. So now what you've done, you've spatially filtered your light, and you can show from an information theory argument that when you mix the two beams back together, there's a net loss of information. And so when you lose that information is the critical spatial frequencies that you're trying to estimate and control, because you're trying to use information from outside the mask to extrapolate the spatial frequencies that are within the mask, which you can partially do, but there's a loss of information there. So there's what I consider a much better approach to doing this. I'll illustrate it for the EPIC, the extrasolar planetary imaging coronagraph. This was just, CAD models, and we did what's called an integrated mission design center study, where you get about 30 or so engineers and scientists all sit together in one facility, and they have mechanical, optical, thermal, electrical, all the different disciplines, and each one has a workstation. And for 1 week straight, 8 hours a day, you go through this design exercise. All the 7 studies have had to go through this process. And you come up with a fairly detailed design, not to the component level though, but kind of the subsystem level, and then enough to cost it out. And so in this design approach, we had a 1.65 meter Cassegrain unobscured telescope feeding a VNC, or visible line chronograph, which is this box here, which is about a meter on the side. It's a little complicated, but you can kind of break it up into subsystems. This whole region right here is really just for the pointing. Since the telescope's dithering around, there's a fine steering mirror that works out of phase with that jitter. And you just have to feed back to that and hold it stable to about a milliarc seconds. Now we know how to do that, because Hubble on any given day is stable to 2 milliarc seconds, and that's in low Earth orbit. So that's fairly, well, I don't want to say standard, but it's been done before 20 years ago. It's 20-year-old technology, more than 20 now. But the critical thing is this optical bench and this optical bench. So this is a shearing Mach-Zehnder nulling interferometer. So that's the critical component. All the stressing technologies are associated with this bench here. So if I kind of break down what's on that bench to a very simple kind of cartoon model, we have the light coming in. It's just 2 beam splitters which are matched to each other. And half the light goes around this way, half goes around this way, and recombine, and you end up with 2 outputs here. Now, if the light coming in is on axis, and then I pull this arm back a half a wavelength of light, that means all the light will come out this port, and none will come out this port of the interferometer. If I was basically to modulate or move this back and forth, I could change which arm the light's coming out of, and they'd be in quadrature, they'd be out of phase with respect to each other. But now if I come in off axis, the planet light comes in slightly off axis, 100 milliarc seconds, that sees an additional phase shift or a different path length going through the interferometer. So its light would come out differently between the 2 arms. So if I tune this such that on-axis light all comes out here, then the off-axis light would come out here. So it separates the photons from the planet, from the photons from the star, into 2 separate channels with 2 separate ports. And the transmission function projected on the sky looks like this. So what that means is if the star is here and the planet's here, all the light is transmitted out to this arm, and none of it's transmitted to the other. If I was to move off that peak, then it would go the other way. So this is projected out, and it's just a pattern. It's not really there. It's conceptually projected on the sky for how you actually detect the planet. Now, if you didn't know there was a planet in the star system, yet what you want to do is vary the spacing of the peaks in the X and Y and the rotation. And so by each one of those variations gives you one Fourier component of your true transmission function, which is this function here. So what you really want for a true transmission function is something which is very sharp at the edges, goes to 0 where the star is, and goes to unity outside the region of the star. And so with 12 Fourier components, you can get a pattern that looks like this. But of course, if you know that once you've found the star, when you do the characterization of the spectroscopy, you just tune the shear and the roll such that the planet sits on one of these maxima. And then you can integrate forever and do your spectroscopy. So then you would get all the highest signal of those. And now I think I have this on the next chart. This just sort of, it shows, that it works. You can do this with a segmented aperture. If you start off with an aperture pattern like this for a glass, the 9.2 meter, if you shear one, you shear it in X through the interferometer and shear it in Y, you'd end up with a final aggregate aperture that looks like this. And then you put it in wavefront across there, you actually can, get your leakage point squared function. But this is better, that's lower down by better than 10 orders of magnitude, actually, in there. And so the sensing and the control now becomes critical, but in a different way. We don't care about the absolute wavefront error. The whole telescope is, say, shimmying back and forth at 100 hertz. This image would be totally unchanged. However, the difference between the segments, because when you shear this over, one segment's mixed against another, so the difference in the change between the segments now starts to matter. So it's a differential approach, which is generally easier. And it's easier because if you have random errors, like a PSD of random errors is like 1 over 1 plus f cubed, where f is the spatial frequencies on the mirror surface. Now, if you shear something, that's equivalent to taking a derivative. When you take a derivative of a function and calculate its PSD, that is f squared times 1 over 1 plus f squared, f cubed. And so that means that the origin now, the sensitivity's gone away. So now you've pushed all your sensing and control further out in the frequency space, and you don't care about the DC drift. So now the system is insensitive to all the thermal and everything in it. You only care about the differential drift between segments as opposed to the whole drift of the system. I'm not going to go into a lot of details on this, but from the advantage of sensing and control approach, though, is now you have an interferometer. And what's an interferometer used for in the lab? Testing optics. So you don't have to have fancy, complicated nonlinear control, sensing and control algorithms because it's sensing its own error as part of the process. So since you have an interferometer, all you have to do is those actually 3 outputs because we use 2 in series. And the sum totality of the photons from all the 3 output detectors is conserved. So it's unity. So that means all your photons, independent of the state of your instrument, are available for sensing and control. They're not absorbed or reflected off the mask, nor is their spatial frequency content modified. That's kind of like an optimal, or a much more optimal control approach for this. So in space, we can control, at a few tens of hertz. This is just kind of a high-level cartoon of this process. So if you were to slew to a new target, and you have some settling time, when you slew the wavefront arrow, the contrast, the flux ratio is destroyed. It goes way up, it gets really poor. And then you have to start controlling and bringing it back down. And so you get a null down here, you allow it to drift up to the mean plus 3 sigma, kick it back down, and keep doing that. So when we did this whole scheme, we had Lockheed Martin actually build a thermal structural optical model of the telescope plus the VNC. We iterated that because we wanted to know how long we could observe between control steps for a fairly standard non-stressing telescope. And the answer was a couple of thousand seconds. So we could actually go, in theory, half an hour uncontrolled if we were in a very benign orbit like L2 or drift away, not in low Earth orbit. So if we were far enough away from the Earth, you could, control every, few hundred seconds or something like that. Now to prove this works, we were funded, we wrote a proposal 2 years ago to build a test bed. We were funded by headquarters, and we have got multiple IRAD, 3 years of IRAD from Goddard, plus a couple of million from headquarters to actually build this up as a scheme. Now this is actually a photograph looking down on the test bed. It's about this big. It's 36 inches by 24 inches. It's 5-inch thick stainless steel plate here that it's on. The whole thing gets picked up and slid into a vacuum tank. It operates closed loop in a vacuum. So this matter of fact, this is only one layer of it. There's actually another layer on top down this. It has the cameras and some of the other pieces on it. But you can't see everything on it when it's on there. So the light comes into a fiber feed and there's a light trap because we have to be very careful with stray light. So this is actually a baffled tube with knife edge, sharp rings inside it and a collimating lens. And then it's totally sealed. And then at the output end, it's just a small aperture, 1 centimeter in size, and then the light is collimated, comes out. Now, there's actually a polarizer here. It's actually in the end of the tube, but it polarizes the light linearly out of the plane of the paper because we want to be transverse electric on all our reflections. The light comes around, hits the beam splitter, splits, goes this way, splits, goes that way, gets recombined here, goes to the bright output channel, and goes to the dark output channel. This is a deformable mirror. We've had 5 of these made through phase 1 and phase 2 SBIRs, and the last one, the final one was just delivered last week. We had one that Greg made the Leo stop for, which was really nice actually. That actually goes, initially we were putting it in front of the DM, but now we have it in a re-imaged beam back down here. Let's see. The deformable mirror, though, is a very special type. It's a MEMS deformable mirror. It's not continuous phase sheet. It's a whole bunch of little hexagonal packed segments in there. This is all ultra precision mechanisms and stages. And then the dark output feeds an EMCCD, an E2B L3 photon counting chip, 512 squared. It's 3-stage Peltier cooled. We have that custom built also. And then this feeds a CMON, 16-bit CCD camera. And we frame out both cameras at 66 frames a second and feed back in closed loop. This is just a cartoon of the same thing. This shows it inserted in the vacuum tank here. Now, the purpose of the vacuum tank is not so much that we need a vacuum, it's acoustic coupling. So the lab setup in cartoon form, actually I can't get far enough back without hitting the wall to take a good picture of the whole thing. Because it's a pneumatic table, and there's active isolation on the table, and then there's passive isolators under the feet of the tank. There's passive isolators inside the tank. And then basically we shut the door and we pull a weak vacuum. And the vacuum is to get rid of the acoustic coupling, because that's our number one thing that we're fighting in the lab environment. We see vibration, people walking around in the building. You can see, we run this for 14 hours or so. You can see when you open the lab door to go home at night, and when you come in the morning, you see the building cool down at night and the clock is moving around. So these are some of the critical technologies. So this is why we need a Leo mask, because this is the deformable mirror. So each one of these segments are 606 microns on a side. Now these are our 3rd generation ones. Initially they were 10 microns thick, a single crystal silicon. But when we move the segments, well, each segment's on 3 actuators, biomorph flexures. You can move them around so they can piston, tip, and tilt. And they're 16-bit electronics. It's quantized to 15 picometers. So these are ultra-stable mirrors. But what we saw is at the edge, we saw print through from the bond points on the back, and then we saw flexing at the extremes of the range. So the vendor IRIS-AO went to 20 micron thick segments, the print through went away, but we still saw some flexing. The requirement is 2 nanometers RMS per segment, the flatness of the segment. Then they went to 50 micron thick segments. The stiffness goes as a cube of the thickness. So we're about 125 times stiffer. And now we see no flexing or so. And we also went from 12 to 14 to 16-bit electronics. So this is actually the mirror we're using now. I photographed it with black cardboard up here because normally it just looks like a hexagonal surface. When I photograph it at an angle with the cardboard, I can see the segment gaps between them. How large is it? 1 centimeter or so. It's all vacuum compatible. It's very fast. Its resonant frequency 6.8 kilohertz. So we have a real-time operating system using a 12-core Lenox box where we do all the drivers for that, and we feed back. It's multi-threaded, So we control it in 32 channels simultaneously. We feed it a clock signal at 6.8 kilohertz, but we're only really controlling it about 15 hertz when it's all said and done. And then, okay, so now if you have this in one arm of the interferometer, now that's controlling the differential wavefront between the two arms. You don't care about the wavefront coming in, so if you're making a phase conjugating interferometer, that's what you're doing. So it's conjugating one arm relative to the other. But you need two things, or three things for phase conjugation. You need amplitude, phase, and polarization. So this only corrects phase. So how do we correct amplitude? Well, if you had a DM in both arms of the interferometer and you feed them against each other, you can control both amplitude and phase. The problem with that approach is it requires twice as many control degrees of freedom, and it's mathematically kind of hard to do it and make it work. And so we came upon another solution using what's called a spatial filter array. So this device here, actually I'll show the next slide and that illustrates how this works. So you have two beams coming into the interferometer, and then they're recombined, and then at the output, you put this device on as a spatial filter array. It's an array of single mode fibers, and it has a lenslet at the input and the output side. So geometrically, it's a device which does nothing. Just light goes through and just comes out. Now, the problem is, now if you have high spatial frequency wavefront error, that's not modally matched to your TEM00 mode, so to speak, of your fiber. So it gets filtered out. You get a small loss in coupling. That's a small fraction of 1%. So no matter what goes in, you always get a Gaussian beam. So you've decimated your beam into a whole bunch of little Gaussian beamlets, and the mean error over each one just shows up as a piston delay between them. So there's one fiber to each one of these DM segments. So this is mapped to this. Now if I move this mirror and piston, I can cause this to catch up to this one because there's not a DM in the other arm. So that actually does your wavefront control just by converting, decimating the pupil into a bunch of beamlets. It's passively filtering the high and mid-spatial frequencies, and then you're correcting just the piston difference. Now, how do you correct amplitude? You sense, at the output here, which one of these little patches is the darkest, and then you tip and tilt this segment to slightly missteer the beam on the end of the fiber to vary the coupling efficiency, and that balances the amplitude. So you have one deformable mirror that controls amplitude and phase simultaneously. Now, we're on our third generation one of these. Everything that shows an image through, we have 3 dead fibers. But what we found was, there's a lot of manufacturing tolerances problems here when they make the fiber bundle. A company called Fiber Guide in New Jersey made it because they made a number for these for their ABL program in Lockheed Martin. But our requirements are much tighter than that. And we find that even just rotating the gravity static fibers, we see the phase shifts in there. So these are actually made where they take a piece of silicon, polish it flat on both sides, etch pinholes at the location of each fiber. They make one for the other end that's matched to it. Then they make Pyrex spacers and another silicon wafer, 7 silicon wafers and 6 Pyrex spacers. And then you basically strip the buffer layer off the fiber, thread it through by hand, and then you tack bond it on the other end. Then under light stress, you tack bond it on the other end such that it doesn't touch the inside of the tube anywhere, which is a very tedious process to do from somebody. But they've done it. And then when it's all said and done, the fibers, of course, are sticking out in the end. They polish the whole thing flat, then the AR coated both ends. And from front to back, the parallelism is 2 arc seconds or so. And we have to place the fiber and location to plus or minus 200 nanometers. And then the lenslets are custom made by an etching process. There is no air in here. This is a piece of glass. And what they do is you can either use bumps or you can etch pits. Now, we've had both done. The bumps are not very precise because you have to control the radius of curvature and the conic constant. You pretty much get what you get. But by using a lithographic process where they etch like cuneiforms or binary optics in the pits, they can actually make lenslets which are in this form. And that It's a much better process. Then you backfill that and then polish it flat. And then you get your conic constant of -0.5, which is ideal for the coupling into the fiber there. So we had five, JPL made us one, University made us one, and then Fiber Guide made us one. Now we have a phase 2. The Fiber Guide one works fantastically, but except for thermal drift and when we move it around and so on. But it's not very broadband. So now we want to make this broadband. So how do you do this broadband? If you were to just use a single mode fiber at the short wavelength and it starts running multi-mode because it's very sensitive to misalignments. So if you went shorter than 500 nanometers, but if you go long wavelength, the mode overlap integral, the core of the area disk is growing linearly with wavelengths, so your coupling efficiency falls. So you end up with this kind of, pass-beam shape in there. Now, if you took the fiber, tapered it down, and expanded it out, a mode scrubber, you can take out that sensitivity, but you get a trade space with coupling efficiency versus wavelength. But the real solution is not to use fibers at all, is to use waveguides. So we have a phase 2 with another company to lithographically etch the waveguides in 3D. Now the advantage of the waveguide, of course, is we don't need the lenses, because now we flange the edges of the waveguides into a feed one. And so now they're all monolithic pieces, all totally made out of silica on silicon, and then there is no lenslets. And so that was supposed to have delivered in November. They've been working on it for 2 years. They delivered us a 1V1, which we tried, which works reasonably well, but it didn't meet all the requirements at the time. So look at how this, well, the other piece is the wavefront control, but I won't get into a lot of details. Well, I can just kind of say that, when you're controlling in the lab, this is why I get this dark hole. The advantage of that fiber bundle with the DM now is the sensing control algorithms are trivial, right? Because you look at the output of an end of a fiber, you're either getting light or not, and you're feeding back to the piston tip and tilt for that DM segment. You have 3 numbers which map, one number which maps to 3. You just mutate it in a 3-dimensional space and drive it to 0. So each fiber and each DM is an independent sensing and independent control system, and they can all run in parallel at a kilohertz, basically. And the advantage in the you can use this in the atmosphere is because in the atmosphere you want to correct the turbulence, but you also want to correct scintillation. So this allows you to sense and control both simultaneously with one device. These are some of our earlier results. So this was, well, the other piece is to make it broadband. That's much more subtle. Initially, in the arms of the interferometer, if you put in glass plates at different angles, you can basically trade off the chromatic lateral color versus longitudinal color, and you end up with a whole bunch of shifted beams with color, but they each travel slightly different path lengths. And then, so that 2 pi over the wavelength times the path length is equal to pi. And you get a bunch of 0. If you use 2 glasses, you get 2 0 crossings. If you use 5, you get 5. But the problem we found with that is that no one can meet the requirements on the strider in the glass. Not only can they not meet them, there is no facility I know of in the world that can measure them. Because people typically measure their variation in index to 1 part in 10 to the 5th, maybe 6. But we have to be able to put specs on it at 10 to the 8th. So it's 2 orders of magnitude better than the current technology. Then we looked at using cross-Braun prisms. If you use Portland-Turner reflection, that reflection is achromatic. So if you have one this way, and then the other one clock 90 degrees in the other arm, you get S minus P and P minus S polarization. But that's actually the same as a pi phase shift. And actually, it's just an equation from Born and Wolf. You can pull that out of it. But no vendor can make the angles on the prisms. We need 2/10 of an arc second. So the cost of that was really high. And then the third approach, which is really promising, is coatings. So we've been talking a lot with JDS Uniphase to make some custom coatings. We have a couple of consultant at the University of Arizona was doing the coating design. So the idea there is instead of treating the glass plates, what you do is you have the 3 reflections in each arm of the interferometer plus the beam splitter. You build a thin film coating dielectric stack with the correct angles between the mirrors. And now, such that when you reflect the plane wave off it, you have two separate specs. The phase shift is pi, independent of wavelength. So when you do that, in theory, you can design coatings. The question is, can you get, manufacture them to the level you need? We still don't know that. That's really an open question at this point. So this is when we were doing, this is without the DM, and this was open loop. So when we first put the interferometer together, this shows the bright and the null channel, both in pupil space, not focused. And so, and this was using the achromatic phase shifters. In open loop, this is dancing around. So if you were to look at this on a monitor, you see when this one goes dark, this one goes bright, and it's kind of dancing in and out of phase. No real surprises there other than we used white light. We were getting a contrast without control of about 1 part in 16,000, or a little better than 4 orders of magnitude. And then we put the DM in. This is an older DM with 37 segments. And then this is the bright output and the dark output. You can see the problem on the edge segmentations. The flexing here causes light to come through. And these are like 6 or 8 nanometer RMS per segment. So they were about 4 times too loose. And then this shows it undergoing control. That's just the logical square of the control metric. And we got it really robust. Eventually we can, even when it was acquiring and bringing it in, we could bang on the table and it would stumble, lose lock, and recover. And this is one Maxine, he picked up a textbook and dropped it on the table and it stumbled. You can see the impulse response of the controller keeps going down. I think this is running, it's a few hertz. I guess it's 15 hertz. So it's running there. So eventually, we got these very clean, so we can control and hold this. And when you're in the lab there, we can give you a demo of this. You can bang on things and stumble and it'll recover and come back. Then if you bring it to focus, now this was before we were controlling from the focal plane. So now when you bring it to focus, you end up with a dark hole, which is what we're after. So these bright things are speckles, bright and dark speckles. This is with a photon counting, EMCCD camera. And so this hole here is dark. The best points are close to 10 to the minus 8. If we extrapolate it out with our requirement of 2 lambda over d, which is about there, we've already hit our first milestone at 10 to the 8. But we haven't actually measured it at that point, so we're not claiming we've hit it. We'll hit that in June of this year, actually. By definition, we have to hit it by June 24th. That's our review panel meeting. So we will, one way or another. And this is, it's not, we're not using lasers, of course. We're using a super continuum kind of coherence source. There's a lot of reflection, so if we use a thermal source, we don't get enough light. A laser is too narrow a band. It's easy to null with a laser. It's hard to null with a thermal source. So you got to use these super continuum, pumped photonic fiber sources from coherence to drive this. I guess I'm nearly complete. Let's see, this is sort of our status chart here, but we had a 2-year development. We were funded 2 milestones, 1 per year. We're just coming up on our first, and then our next one will be next spring or so, 10 to the 9 narrow band. Then the next TDM has 2 more milestones. One is this is the 3rd generation nuller we built. The 4th generation now shrinks. This has metal in it. The new one has no. It's just a design, and we procured the glass, and they've rough polished it and cut it, but cut it and rough polished. They haven't done the final polish. But it's all shot with the silica, silica of the highest grade. So they take 1 block, melt, and they hog out all the pieces for the interferometer. Every mount, every piece is made out of the same material. The reason why you do that is because when you do the structural thermal optical design, you want it insensitive to bulk temperature shift. So if you build the interferometer correctly and the temperature goes up 10 C, then both arms of the interferometer grow at the same rate. And so it's an athermal design, and then becomes only sensitive to X, Y, Z gradients in temperature, but not even static gradients, just the temporal rate of change of those gradients. So the 3rd and 4th milestones are associated with that nuller, and it was a compact nuller. That's the first one we want to try out on the ground telescope also. So we're trying to actually package this up for a ground instrument box to try a 1 meter and then a 3 meter at Apache 1.5 point will peak in, I think it's New Mexico, so we're just starting to talk with them to do that. This was Maxine, a summer student I had having fun controlling the DM. We could actually write an answer and do it by using the null. I pretty much said that. And this is the final here. So someday, if we're lucky, we may even find life out there. It'll be-
That's nice.
Well, thank you.
Thank you.
Any questions?
Okay, I have a question. I mean, first of all, thanks. That was fun to talk. Can you explain how important it is to drill those masts, pretty much to do the masts, the pinholes to that accuracy that we have here, or that, so you had the mast from Huron, right?
Yeah, let's see. So you want to see, these segments are, 606 microns flat, 613 microns center to center, and they're plus or minus half a micron, or 500 nanometers, and they're made, it's a MEMS process, lithographic process in there. So we want the edges of these very clean, but of course they never are. So what happens is the main limitation, the stack up of the errors doesn't occur in the center of the segment, they occur around the edges. So we have to measure what that stack up of errors is, and then make a mask, which masks out that region. And so that's the mask that Greg made. So the first one, they were circular holes. Now the reason why we just use circular is just because they were the easiest. But in reality, if you use circular, we're throwing away light, and the photons in space are really valuable. So we don't want to do that. So ultimately, you want hexagonal mass, or hexagonal with little rounded corners possibly. And you're going to want to make the mask, almost photographically. You're going to have to, photograph this surface and somehow measure this surface where all the gaps are using, say, confocal scanning microscope or something, and then actually make a mask, which is very extremely well matched to that shape. Now, what does that do if there's errors in the mask? If you look in this, I can describe it here, but I can't see it at this scale, but you can kind of see there's little flares, brighter and darker coming out. So those are diffraction flares due to little junk or little structure around the edges of the holes or around the edges of the segments and the segment gaps. Now, since all diffraction is asymptotically theta cubed on the sky, or 1 over theta cubed, so if I had something out, a diffraction structure which diffracted out here, it also diffracts inwardly and falls off as the theta cubed. And so as you start adding up all those little errors, it starts, lowering, raising the floor of that dark hole, which means you're losing contrast. And so I don't have a good sensitivity number on it. Matter of fact, when we first did this, the Leo stops were one of the things we kind of neglected because we thought this was an easy, well-known technology, but it turns out it's not. We're not the only ones finding this out, because everyone thinks, oh, mask, how hard is that? It's just a bunch of holes. But it's making precision holes in good locations. It's not trivial.
Thank you. The third approach in the telescope,
Da Vinci.
huh?
Da Vinci.
Da Vinci one. So years ago, he called in, he needed a mask.
Oh, Mike Shaw.
Mark Shaw.
Oh, yes.
And he wanted to do it the old way, like we were doing, the larger holes, the smaller holes. So what are you doing that for? Because intensity is like
Yeah.
before orders of magnitude thousands. So what do you expect us to do? So instead we just make him the same hole diameter, but different number of holes in different location. And that's simplest technology because again we reach the highest repeatability there.
and it worked perfectly for him because he could do the binary counting pretty much. He knew X number of codes there, but by air, he was extremely happy he was able to do the,
You know, we need something similar. I mean, we have the new DM, and now it's in, when we get the new DM, and it's shipped to the microscopy lab, then they have 3 different types of microscopes they look at. They measure all the edges, locations, and center to center. They have a map of that surface, and the coating it. I mean, we've seen problems in the earlier ones, like the outer ones, you could actually see the coating strips, you know, like the edges around the segments and so on. Coating them is not